Okay, so I would like to welcome everybody to this series of seminars which are organized between Brazil, Argentina, Portugal, and it's my great pleasure to have today Marielle as our speaker. So Marielle, I will just do some very quick introduction to you. So you finished your, now you are a researcher in INRIA in Lille, and you finished your PhD in 2014, right? In ENS with the supervision of Stefan Owola and Cedric Bernardin. Then you did a postdoc with me in the PUC in the Catholic University. I hope you have enjoyed it.
Yes.
And now you are leading this team with this ANR project, which is very, very nice. And I hope you can visit us in Lisbon. It would be very nice to have you. Well, maybe February, who knows? And today you're going to give us a talk about hydrodynamic limit for a facilitated exclusion process. Thank you so much for accepting the invitation, and the floor is all yours.
Okay. Thank you very much, Patricia, for this nice introduction and for the invitation. So please, of course, interrupt me if you don't hear me well or if something is not clear. It's not easy to make a seminar in this distance way. So please don't forget to interrupt me or to write in the chat. I will check it. Okay, so I will talk about a result which is about the facilitated exclusion process, and in fact it is a work in collaboration with Oriane Blondel, who is in Lyon, Clément Erignoux, who is now in Lille with me, but he also spent some time in Brazil, in Rio, and Makiko Sasada, who is in Tokyo. And this work has been published in 2 separate papers that I will explain why in a minute. Okay, so the facilitated exclusion process belongs to the class of one-dimensional exclusion processes. Just recall some of their properties. So there are particles on the one-dimensional lattice, and at most one particle can be present at each side. So the configuration of particles is represented by eta, and eta j of t belongs to 0, 1 for any t. 0 meaning that there is no particle, and 1 there is one particle. Okay, and we assume in this talk that boundary conditions are periodic. Okay, and the exclusion processes, one of the main important features, and that they preserve one quantity, which here is the number of particles. So the sum of eta j is preserved along time evolution, along the dynamics. And this conservation laws gives rise to a family of equilibrium measures, which I will denote pi rho in the talk, and they are usually parameterized by the density rho coming from the conservation law, parameterized by rho being between 0 and 1. And for instance, the pi rho satisfies that the average number of particles per site is equal to rho. Okay, so rho is the average number of particles that you find per site. And what I'm going to define is what is the dynamics followed by the particle. It is a Markov process with jumps. And these processes, in fact, are quite rich, because there are a lot of ways to compute the jump rates, and I will give one of them. Okay, so I'm going to define now a Markov process with jumps on this particle system. So as I said, the state space is n sites in one dimension plus periodic boundary condition. So eta lives in this 0, 1 to the torus Tn, and the generator of the Markov process is simply given by the sum over j of some jump rates Cjj plus 1 of eta, and what happened when you exchange 2 neighboring values eta j and eta j plus 1 on local function f. So eta j plus 1 is obtained after the exchange of eta j and eta j plus 1. So this means that particles can jump only to their neighbors. And Cj plus 1 is the rate of the exchange. Okay, so this is let's say the general way to define one type of exclusion processes. And the exclusion is encoded, the exclusion rule, the fact that there is only one particle per site, is contained in this Cjj plus 1. So for instance, for the simple exclusion process, the most simplest exclusion process that exists, Cjj plus 1 is given by, so either there is a particle at J which jump to J plus 1. So there is a particle at J which jumps to J plus 1. So the site J plus 1 needs to be empty. Or there is a particle at J plus 1 which jumps to eta J. So this is the rate for the simple exclusion process, which has been very well studied in the last years. And another type of processes which belongs to this is the kinetically constrained exclusion lattice cases. So you can also add, so this means that you add kinetic constraint, which will be added in the jump rates, okay, in Cjj plus 1. And this is the family of models to which belongs the facilitated exclusion process. So in fact, now I'm going to introduce these kinetic constraints, and the constraint dynamic that I'm going to define has been proposed, in fact, to me during my postdoc with Patricia. Patricia told me about this, and was quite interested to study. And you see, we are still working on it. So, and the dynamics is as follows. So as before, the particle can jump only to one of its neighbors, so either J plus 1 or J minus 1. For the simple exclusion process, these two jumps are possible because the neighboring sites are empty. But in the facilitated exclusion process, the rule is that the particle to jump to J plus 1, for instance, it has to be pushed in some sense by the particle at J minus 1. So to perform the jump, the particle needs another particle next to it. So this jump is not possible because this site is empty. And this jump is not possible because this site is empty. Okay, so the particle needs a particle to jump. So for instance, the only jumps which are possible are the ones where particles are together, if you want. So this can jump, also here and here can jump. But you see that there are particles that cannot move at all. So this one is totally blocked, cannot perform any jump. So the jump rate, now you can write the jump rate in a similar way. So if the particle wants to jump from J to J plus 1, so you need a particle at J, no particle at J plus 1, but you also need a particle at J minus 1. So you put an eta J minus 1 here. And now there is the other way, or there is a particle at J plus 1, no particle at J, but you need a particle at eta J plus 2 to jump. Okay? So this model is very rich, in fact. And I will now explain why. So this eta J minus 1 and eta J plus 2, if you want, it represents the constraints that you add on the dynamics. Okay, so first observation to this on this dynamics, they are completely frozen configuration. So if all particles are isolated, are alone, okay, so you have particles here, 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 no jump can be performed. So the dynamics is completely frozen, okay? And particles do not move anymore. In fact, this model belongs to the class of, for those who know, the class of cooperative models, which means that there is no possible mobile cluster which moves particles around. Okay, you cannot find a group of particles which will allow the other particles to move anywhere in the lattice. So there is no mobile cluster, for those who know this kind of property. And the invariant measures in this model quite, let's say, it's quite specific that in this case, the invariant measures are not the product of Bernoulli measure. They are not product of Bernoulli measure, as it is the case in a lot of exclusion processes. Okay, they are much more complicated here. You can check that they are not invariant.
Marielle, sorry to interrupt. There is a question in the chat. Can you see it?
Sorry. Maybe the space between the two middle has to be 2 as well in the drawing. This configuration is completely blocked and cannot move.
Okay, so there is something I don't understand then. The middle particle, the middle particle, it can jump to, I mean, okay, let's say that I thought that to jump you need one neighbor on the receiving particle. You need one neighbor on the receiving side or on the departure side to be full?
On the departure.
Okay. This was the point I was not getting. Thank you.
Yeah, exactly. So there is the other case where also a neighboring particle in the arrival site is allowed, and it is I would say it is close to the porous medium model, also studied by Patricia and Claudio and Cristina, but it is quite different, in fact. So here now, only one empty site in the middle of 2 particles is enough to block everything. Okay, good. And in fact, this model is also not, so this Markov process, is not irreducible on, even if you fix the number of particles, you don't have the irreducibility property that you usually have in exclusion processes. So you cannot change any configuration into another, even if the number of particles is the same. And in fact, here we will see a phase transition at a critical density, which I will give right after the critical density. Okay, and the macroscopic behavior, what we will obtain as a macroscopic behavior belongs to a free boundary problems. And the free boundary means that, in fact, you will see a free boundary moving between the regions where the configurations are blocked, and so the frozen regions and the active regions where a particle can move. Okay, so this is what I'm going to explain. So what is the main goal of this investigation? Let's say that to prove hydrodynamic limits, which means that, so we assume that at initial time, there is a form of local equilibrium, so that the particles are distributed on the lattice according to a profile, which is rho initial here. And we assume that the empirical density for the particle system converges as n goes to infinity to this rho initial. Okay, so here we can put the integral on the torus. Rho initial. So we assume this at initial time, and we want to obtain the same behavior in some time scale. So here we investigate the empirical average in the time scale, which in this case will be the diffusive one, but sometimes it's not the case. The diffusive time scale, and you expect that this also converges to some profile, which now depends on T, and which is solution to a PDE. So rho at initial time is given by rho initial. The initial condition is fixed, and rho is solution to a PDE. Okay. Which is called hydrodynamic equation. And before to give the PDE that we get, which will be a free boundary problem, let me now explain what is the critical density and why do we expect a free boundary problem now. Okay, so the critical density is 1/2. So with the several drawings, we will be convinced that it is quite obvious. Okay, so assume that you have a number of particles which is less than the half of the number of sites. So you have two possibilities. Either all particles are blocked. Sorry, I put the sites. Okay, so you have a few particles and they are all blocked. Okay, let's say 4. So this is what we call frozen configuration. But there is also one other possibility is that, okay, so maybe there are very few particles, but some of them can be closed. For instance, the first ones. But after a jump, after a few jumps, the particle will become blocked, okay? So it needs only one jump here and the configuration becomes blocked. So in fact, these are called bad transient configuration. And why is it transient? Because in fact, after a few steps, these configurations will enter into the set of frozen configuration. Okay, so for now, K and N are fixed. Okay, so you only need a finite number of steps if K and N are fixed. And with probability 1, the configuration will become frozen. And it is exactly the same kind of thing which happens now if K is bigger than half of the sites. Okay, so you have now particles which are much more. You have two possibilities. Either, so now this is not the particles which will be isolated. This will be the empty sites. So you can only find one empty site in between two particles, not more. Okay, so this is where I will write it here. Empty sites are isolated. Okay, and these configurations, in fact, are the ones on which the dynamics is irreducible. So this, which we call the ergodic configuration or ergodic states, this is because the dynamics restricted on this set of particles is now irreducible. When you fix the number of particles and you assume that all empty sites are isolated. So this is the let's say the good set of configuration on which we expect an irreducible dynamics. And if it's not the case, so now you have a lot of particles, but maybe there are two isolated sites, two empty sites, sorry, which are close to each other. So these two empty sites now are close, but after one jump, this configuration will enter into the set of ergodic states. So these are, let's say, good transient configuration. Okay, and when I say that, okay, after a finite number of jumps, the transient configurations will be either frozen or ergodic. Of course, this finite number of jumps here depend on N, on the side of the system. Okay. And in fact, we have to estimate the time the dynamics spends into these transient configurations if we want to if we want to be able to prove some hydrodynamic limit properties. Okay, because if the dynamics stays in these transient configurations in time which is very big, then the microscopic behavior which will be much more difficult to understand. Okay. So you see now that really the critical density is 1/2 because above or below 1/2 you are either completely frozen or completely ergodic. Okay. So what are the invariant measures now? In fact, so I said that the invariant measures are not the product of Bernoulli, but they're not that complicated, in fact, because after some combinatorics arguments, you can find them quite easily. So, of course, the invariant measures, you have all the Dirac measures concentrated on the completely blocked configurations, but they are not really interesting here. Okay. So I'm going to talk about the invariant measures only on the ergodic component. This is the interesting set of configurations. So if now we look on the set of configurations with exactly k particles and they are all ergodic, so which means that, remember, all empty sites are isolated. On this set, the uniform measures are invariant. Okay, for the simple exclusion process, it is the uniform measures on the set of particles with k particles, which are of configuration with k particles, which are invariant. Here you need to also assume that empty sites are isolated. And they are also reversible, in fact. Okay, they are invariant and reversible. And we can compute a lot of things with these invariant measures, because in fact, it is only combinatorics. You need to compute how to put empty sites in the interstice of particles, in the middle of particles. Okay, so you can compute, for instance, the cardinal of this set. Since you want to have access to the uniform measures, what is important is in fact the cardinal of this set, and you can easily check. So think about putting empty sites in the middle of particles, and you will see that this cardinal is, so you have n minus k choose k plus n minus k minus 1 choose k minus 1 possibilities to have these configurations. I will not detail the computation, but it is very, very easy. Nothing hidden here. So if you can compute these kind of things, in fact, you hope to have access to the grand canonical measures now. So not fixing the number of particles, but now you want to fix the density. So when k over n tends to rho, and you assume that rho is bigger than 1/2, so we are on the ergodic set. So these measures, in fact, converge. So these measures converge to converges to some pyro. The grand canonical version of the invariant measure, so grand canonical. Okay, and you have a lot of properties of pyro, and I will also describe it very well right after. So pyro, in fact, you can check that it is translation invariant. And in fact, pyro is what, if you think about exclusion processes, the simplest one. In fact, pyro is a Bernoulli product measure, but conditioned to only ergodic configurations. So in fact, pyro is a Bernoulli product measure with condition to have only isolated empty site. To having isolated empty site. Isolated empty site. Okay, so it is not product, but it has also a structure that we can understand. And one of the property of pyro is that, in fact, it has long range, so correlation, which can be quite long range if rho is very close to 1/2. Okay, so we have to be careful about this correlation when rho approaches the critical density 1/2. Okay, and if you want to even more details about pyro, so what is pyro? In fact, it is not product, but pyro put a number of particles which are neighbors as an geometric random number of particles. So let me be a bit more precise. So if under pyro you have an empty site with a neighboring particle with probability 1. So this happens with probability 1 under pyro because you don't have the right to have two empty sites which are closed. Okay, so if you have an empty site, then the particle next to this is here with probability 1. And then the particles which follow, they are distributed according to a geometric law with some parameter, and the parameter will be 1 minus rho divided by rho. This is also something that you can check with combinatory argument. And then you start again with one empty site plus a particle with probability 1 and another geometric number of particles. And all these groups of particles which are geometric are independent. So here you have an independent of these groups of particles. Okay, so if you want a formula, so the probability under pyro to find somewhere one empty site plus L particles, it is the probability to have one empty site times the probability for a geometric number, geometric law of parameter 1 minus rho divided by rho of being at least L minus 1. So you don't know the next site here after L. So you only know that there is one empty site plus L particles, a group of L particles, and this probability under pyro is the probability to have an empty site and the probability for the geometric number of particles to be at least L minus 1. So the first particle does not count because it is here with probability 1. Okay, so the formula here is 1 minus rho. The probability to have an empty site is 1 minus rho times 1 minus rho divided by rho to the power L minus 1 for the geometric number of particles. Okay, so you have access to a lot of things because you can compute things under the probability by rho. The only tricky point is that it has correlations, only this. Okay. This is for the invariant measure. So now what we expect, so what we hope for is to derive hydrodynamic limits. So for example, what fails in the entropy method, which has been used a lot of times. So the fact that the invariant measures are not products, so in fact, it is quite important in the entropy method, but it is not very difficult to extend it to non-product measure, especially if you have controls on the correlations. Okay, so controls of correlations is good, but okay, they're not product, but what is difficult here is also that they have this joint support. If you look on the set of ergodic configurations above one half or below 1/2, okay? According to the critical density 1/2, they have these joint supports. This can be quite tricky, but it's not the main, let's say the main difficulty here. It was not this. The fact is that what was more difficult is that it is not irreducible on the set with a fixed number of particles. So this is not the case. And we have to estimate the time spent in the transient configuration. Transient states, okay, and we have to estimate this as a function of how it depends on n. The size of the system. Okay, so this was one of the main difficulties. Let's say the good news is that at least the model is gradient, and this, I think, this is why Patricia and Christina were quite hopeful when they looked at this, because okay, then they knew that the model was gradient, and it's a good point. And the invariant measures, even if they are not products, they are quite explicit. Okay. Okay, we have a lot of that they are explicit. We will not say quite, they are explicit. We can describe them. So what we expected here is, of course, we knew from the beginning that the diffusive timescale was the right right timescale for the evolution, macroscopic evolution of this system, and we were looking for the PDE satisfied by the macroscopic density. Okay, so the first result that we get now, let me go to the result. The first result, what we get in 2019 was on this transient time. So the time the dynamics spent in the transient component. So we assumed first that the initial profile was uniformly above the critical density 1/2. So this means that everywhere in the system there are a lot of particles. Okay, so the density is always, sorry, the initial density is uniformly above 1/2. Does never cross. So the configuration is let's say is active everywhere, and we wanted to estimate the time the configuration spans into the transient good configurations. And we were able to prove that this time as a function of n is much less than diffusive, and which is good. And in fact, the much less than diffusive here, we have an estimate of order log n to the alpha, which will make sense maybe in a minute for some power alpha, which is not very important. I'm not sure it is the best estimate that we can get on Tn, but it is okay. So what we prove is that the probability under on the space of trajectories, okay, that eta at this time Tn is not ergodic, so it is not in the ergodic state. As n goes to infinity, this goes to 0. So it is ergodic with probability 1, and as n goes to infinity in this time scale, which was completely enough then to obtain the hydrodynamic limits. Then after this theorem 1, let's say this is the most important, theorem 1 is quite important. The step to get hydrodynamic limits, assuming that the initial profile is uniformly above 1/2, was quite, let's say, affordable. It was not that difficult. So once you have this, you can prove that in the diffusive time scale, as I was saying before, the empirical density converges to, as n goes to infinity, to this rho of T U G of U du on the torus. And rho of T is a solution, and a non-degenerate solution, I would say a non-degenerate equation. In fact, here it is a solution of a PDE, which is diffusive and which can be written as so second derivative of 2 rho minus 1 divided by rho with some initial condition. Okay. So here there is no free boundary, no free boundary problem, because the initial profile, remember that the initial profile, assuming that it is always above 1/2, and this equation, this PDE, satisfies the maximum principle. So in fact, rho will always be above 1/2. It always stay in the supercritical regime phase. Okay. So this PDE is not degenerative. Even if you divide by rho, there is no problem, because rho is bigger than 1/2. So it is a strong solution and it is a diffusion, let's say diffusion problem in a strong sense here. There is no problem. So of course, what we wanted to do is to to go to the general case where the initial density can cross 1/2 and go below. And this was the next step. So I didn't emphasize. So the difficulty to pass from theorem 1 to theorem 2 was just, let's say, control. So the correlation of the invariant measures, which were quite let's say technical, and prove the equivalence of ensembles. That is not obvious here because the invariant measures are not product. So the fact that they are not product, in fact, ask for technical issues. Okay. So second step was to assume now that the initial profiles can be anywhere in 0, 1. So I will make a bigger drawing here now. 0, 1, critical density 1/2 and 1. And so the initial profile is, so it is periodic here. So I'm something to put periodic. Okay, this is rho initial. And this is where the critical value is. Okay, let's assume, for instance, this kind of initial profile. Yes. And what we proved then, so we will see, in fact, the free boundary problem. So in the same diffusive time scale, we have the same convergence. So I wrote the convergence here in probability sense. Okay, this is the rigorous way to write it. And the diffusion equation is second derivative of, same as before, 2 rho minus 1 divided by rho, but now there is an indicator function here that rho is bigger than 1/2. Okay, so this means that in the region where rho is less than 1/2, dt rho is equal to 0 if rho is less than 1/2. And it is diffusive, so it is given by this diffusion equation if rho is bigger. This is why there is a free boundary at exactly at the points where rho crosses the critical density. So what happens on this profile? At later times. So when now, so I will draw rho at time t strictly positive. So the profile below 1/2 does not move; it is fixed, and above 1/2 it diffuses. Sorry. So this profile of density tends to diffuse. So you have something which tends to, let's say, be like this. Okay. And it creates a discontinuity here and here, and the profile which is below is completely fixed here. And the free boundaries are exactly this. Okay. This free boundaries between the region where rho is less than 1/2 and bigger than 1/2. Okay, so this is what we call also Stefan problem, and of course now the solution is only a weak solution, but it is enough to obtain what we want because it is a convergence in the weak sense, so it's okay, and it is a solution of the Stefan problem. Okay. So to obtain this convergence, we need to we could not use the entropy method again, but we used a strategy implemented by Funaki, which I hope I will have time to say a few words. And so after the hydrodynamic limits, in fact, we were happy, but not that happy because the weak notion of convergence, in fact, does not say anything about these three boundaries, and we wanted to check if there are some correspondence between the microscopic boundaries between ergodic regions and frozen regions, and the free boundaries that are given by the Stefan problem. So to be more precise, what we wanted to obtain as a, let's say, a complementary result is that, so we added some condition on the initial measures because otherwise we could not have more information on the boundaries. So we assume, for instance, only two, as I have drawn before, only two critical points. So only two critical points where the initial density is initial density, let's say x star, is equal to 1/2. So at initial time, there are only 2 points where the density crosses 1/2. And at these points, the derivative is strictly positive. So this critical, it's not zero, so not positive, but it's not zero. Okay, so to assume that there is some diffusion at time t positive, the diffusive region will move, and the free boundary will move as soon as t become positive. And under these conditions, so for instance, is only because you can also assume several critical points, but let's say only two for now. And what we proved on the microscopic particle system first is that the transience time is also subdiffusive, so it is less than diffusive, and you can really define rigorously a separation between ergodic phases and frozen phases. So let's say that this is x minus n and this is x plus n. So you have a unique and rigorous way to define this x minus n and x plus n, such that this region here is completely ergodic. So it is not transient anymore. In the middle, there are only isolated empty sites, and to the left and to the right, there are all particles are frozen. There are no possible move in this after this transience time. Okay, so you can define really rigorously this x minus n and x plus n after some time, and you can prove that these points of separation coincide with the macroscopic free boundaries. So what you can prove is that this x minus n divided by n at the time in the diffusive time scale tends, so in some sense, of course, it is in probability as before, to x minus of t, and it is also the same for x plus. Okay, so it was x plus and x minus, where x minus and x plus come from the PDE. So these are the free boundaries coming from the PDE. That you have also an implicit way to define them, free boundaries coming from the PDE. Okay, so this will also prove it in the same paper. In fact, it has been published now. So this is why there were two papers, one on only the active phase and the other one on the general case with this free boundary behavior. Okay, so I have some, let's say about 10 minutes to give some elements for the proof of this, and I will start with how we prove the transience time. So in fact, now I will give you another way to see the model. So you can, if you were lost somewhere, or if you were thinking about another thing, you can just start it now, because I will define now a mapping from the facilitated exclusion process to the zero range, which is very interesting and which helped us a lot. So the mapping is this one. It has been used already. It is not new, okay? But you can map the facilitated exclusion process into a zero range. And what you do is that, so first, oops. Okay. So the number of sites in the zero range model will be the number of empty sites in the configuration, in the exclusion configuration. Okay, so on this example, there are 7 empty sites. So you put 7 sites for the zero range, and on each site you put the number of particles in between 2 empty sites. Okay, so of course I didn't put enough space. So here you have 1 particle, here 2 particles, here 1, and 3. There is an empty site because in between 6 and 7 there is nothing, and 1 particle here. Okay, so this is how we define the map from the exclusion to the zero range, which is not unique only if you fix the starting empty site. Okay, you can shift the zero range if you shift also the how you put the numbers in the exclusion configuration. And if you map, if you use this mapping, in fact, you can also map the dynamics. So there is also a unique Markov process associated to this zero range, which coincides at each step to the facilitated exclusion process. So what happens? Let's try to be as clear as possible. So, for instance, the particle on the zero range can jump to one of its neighbors as soon as there is at least 1 particle below. Okay, so since in the exclusion process the particle needs a particle close to it to jump, in the zero range it needs a particle below it to jump. Okay, so jump possible if and only if there is at least 1 particle. So if I denote this omega j has to be at least 2. And in fact, the other, so, and it is an if and only if, because the other particles are completely blocked. The ones which are alone in the zero range correspond exactly to the one which were alone on the exclusion. Okay, and these are the blocked particles. So these particles are blocked on the exclusion, and they're also blocked on the zero range. And as soon as you have at least 1 particle below, so at least as soon as you have at least 2 particles on the zero range site, they can jump either left or right with equal probability. So in fact, the jump rate for omega j of t, so the Markov process for the zero range, is you can check that particles jump from j to j plus 1 or from j minus 1 to j with the same probability, which is that the indicator function that omega j is bigger than 2. And it is a simple zero range process, but it has the same property as the facilitated exclusion process. So it is not irreducible on the set of particles, on the set of configurations with a fixed number of particles. So there is also separation between frozen configurations and active configurations, ergodic configurations. So in fact, what happens is in the zero range is that if so the particle the particle which can jump, and as soon as they fall into an empty site, it becomes blocked. And so the first line acts as, let's say, a layer of particles which is completely blocked, and above the first line of particles, the particles perform a usual zero range, okay, with the standard one, the most simplest one, with independent, so symmetric random walks, sorry. Okay, and on this zero range, you can work a bit more easily, let's say, because you have the invariant measures now, which are products. So, oops, you can check that for the zero range, the invariant measure here are products. They are also given by Poisson laws that, as in the standard zero range process, but you have to impose that there is at least one particle. So it is not the usual Poisson law, but it is quite simple to describe. And so to understand the ergodic configurations in the empty site, in the facilitated exclusion process, sorry. So the ergodic configuration in eta, remember that it was where all empty sites are isolated. All empty sites are isolated. And in omega, it is where there is at least one particle per site. So everywhere omega j is bigger than 1. So estimate the time to enter into the ergodic sets. It is to estimate the time the zero range needs to fill the first line. And as soon as the first line is filled, then the configuration is ergodic. And this is how we estimated the time. So it was used to estimate the transience time, but it is not used to prove hydrodynamic limits because the mapping is not that obvious, especially because it changes the length of the space, okay, which depends on the number of particles. And in the hydrodynamic limits, you don't fix the number of particles, you fix the density. Okay, so using this mapping at the level of hydrodynamic limits, it's much more tricky. Okay, so I will not, because I don't have time now, so I will not detail the proof of the hydrodynamic limits, just to tell you that the model is gradient, so the usual trick can be done, and there's some replacement lemma to prove this at least in the active phase. Okay, so in the active phase, the first theorem for hydrodynamic limits, you can use your usual entropy method, and so you only need to prove correlation decay. At the level of the invariant measure, which here we can prove that it is exponential. Okay, with some constant which depends on rho. So this we can prove, and we have to. So this was not quite simple because of the fact that it's not product. So this is to prove equivalence of ensembles. Okay, this was for the active phase. For the free boundary problem, in fact, so what we used, as I told, was a strategy implemented by Funaki, which was based on Young measure, and it is a more robust, let's say, to deal with the models which have stationary measures, invariant measures which can have disjoint support. So if just to give you the only, let's say, the detailed lemma, and then I stop. So what you need to prove is that you need to characterize all stationary measure. And what you prove, and remember that they can have disjoint support. So in fact, what you prove that all stationary measure in infinite volume, let's say mu bar, is a convex combination of, so it is a convex combination. So there is a coefficient which will be in 0, 1 here, which I will put here lambda and 1 minus lambda here. It is a convex combination of what? Of a probability measure which is supported in the set of frozen configuration. So let's say the Dirac delta, okay. If you want probability measure, I will denote it, I don't know, let's say new frozen, and another convex combination now of the pi row. Okay, so now you have the pi row here for a row which is between 1/2 and 1. But you have some probability measure here, which is on row, let's say sigma of the row, for instance. Probability measure sigma of the row. Okay, so a convex combination of a measure supported on the frozen set and on the convex combination of pi row. Okay, so this is what we needed to prove for the facilitated exclusion process to then implement the strategy of Funaki. But of course, we also need once again to estimate the transverse time as before. And for the Stefan problem, what we needed, which was not obvious for us, was at least for the last result, the existence and uniqueness of the free boundaries for the interface problem of interfaces. And in fact, at least for the last result, okay. And we hopefully we were quite lucky because we found let's say PDE results which gave us what we needed to prove our theorems. So it was one of them was a paper of Mermanov. If some of you are interested. Okay, so thank you. I'm concluding here. Sorry, I'm quite late, but these are the two papers and my collaborators on this project. Thank you very much.
Thank you, Marielle. Thank you so much. So let's thank Marielle. Very nice talk.
Yeah.
So
if you have any questions.
Yeah, questions from the audience.
Of course, I'm also happy to answer to questions by email if you have if you don't feel comfortable to talk in this way. So don't worry.
I have two questions, Marielle. Okay, I'm not sure somebody's. Have you thought about this in dimension D?
Yeah,
this is one-dimensional, right?
Yes. So it is a current project, in fact. But it is much more difficult. So you have two possibilities. For instance, in 2 dimensions, you can assume that, so what we call the FEP 2D, let's say, is that the jump is possible only if there is a particle in the opposite direction. So this particle has only one possible jump, for instance, and it cannot move here, so above or below. And it seems that this 2-dimensional version of the SEP, so we didn't find anything in the literature on this FEP. On the contrary to the 1-dimensional FEP, which was in the physics literature, in fact. So we found some papers on the FEP in 1 dimension in the physics literature, but this version of the FEP, we couldn't find anything. There is another one which is quite similar, in fact, and we also we are comparing the two. Is that so you can assume that the particle can jump anywhere as soon as there is one particle somewhere. So these 3 jumps are possible because there is this one. Okay, so 3 possible jumps. 3 possible jumps. So. And for this one, we called it CLG because it belongs to this conservating lattice gases in the physics literature. They are called like this in the physics. So and this model is present in the physics literature. In fact, physics literature, there are some investigations, let's say, but on the FEP there is nothing. So what physicists do is that they estimate the exponents of these models and to see if they belong to some universality class. This is what physicists do usually. So they're very interesting in this, but there's nothing rigorous which has been proved. And in fact, we are not even able to characterize the ergodic to prove that below 1/2, if the density of particles is above 1/2, then the configurations become ergodic. So we're not able to prove anything about these models for now. And what we are doing now is numerical simulations, basically, to compare these two, to see if we can obtain more information that physicists already have. And but there are a lot of things to do on these two-dimensional versions for sure, because it's very, very difficult to. For instance, the mapping with the zero range is not available anymore. You don't have invariant measures, so you don't have an explicit description of invariant measures, even the ergodic set. And so.
Sorry, Marielle, sorry. In the first picture, if you have a particle below, can you go up or you can just move left and right?
Yes. So particle can jump in the opposite direction.
Okay.
Yes. And in fact, for the FEP, you can see that if you are not lucky, maybe particle will align to some lines, and they will continue to move. No, this is not possible. But they will continue to move only on the lines, and they cannot jump anymore to vertical. So this is not possible. Yes, you see. So you have a strange configuration which are not blocked, but they are blocked on lines. So particles move, but they are blocked on lines. So several FEP, one-dimensional, and so this is a complicated model here.
Great. More questions?
You have a question. Marielle, do you have some comments about the other facilitated exclusion that, for instance, Leibovitz and Spear are discussing, where you have a particle, you need a particle close to the arrival and another particle close to the departure sites?
Yes, so no, I don't have any comments.
Okay.
Yes, I know that there are some really recent papers on this. It is not exactly the same, in fact, and there is also one paper where the dynamics is quite deterministic. No, it is not a stochastic Markov process.
I don't know that.
Yeah. So, but. No, I cannot make any comparison here, but I believe that really these kinds of systems are very interesting, and right now they are investigated a lot. Yes.
Thank you.
More questions?
You
bet.
Hi, Marielle. I have a question. It's quite vague, but are there any interesting open questions for the system in infinite volume?
In one dimension?
Yeah, one or more. I don't know.
So in
one dimension, for instance, if you start from Bernoulli, do you know, is everything known about fixation of the system, or?
This is true. That's I didn't say that we start our system from only from Bernoulli with the product. So a product Bernoulli with the right profile. So you want to start from another initial measure.
You start on the infinite line, say with Bernoulli, and you want to know if the system jumps if particles jump forever or not.
Yes, let me think about if the density is bigger than 1/2, then then the configuration will become ergodic in a very quite quickly. Okay, in the time of the log n of the power alpha, then the configuration is ergodic. So before log n to the alpha, maybe this I don't know what happens.
No, for 1/2, for density 1/2 is
no
interesting case.
The critical density. Okay, no, at the critical density we don't know nothing.
Okay.
But maybe the time the dynamics needs to, for instance, to become okay. I see what you mean. The time the dynamics needs to become one particle, one empty site. Sorry, one particle, one empty site. Okay, would be the critical density 1/2. Would be this one particle, one empty site, one particle, one empty site. No, I don't know how much time it would take. In fact, maybe quite long.
No, how is it in the infinite line, I guess, at density 1/2, how the system would behave if
no, we don't know.
Because it seems if you are exactly at 1/2, it seems difficult to fixate because you might have
exactly
random fluctuation, but
yeah.
Okay.
No, we don't know.
So
yes, the critical density 1/2 is an open question. Yes.
Okay.
No, in the zero range is interesting because you have all these arms to fill, and you start with the product Poisson with mean 1.
Yeah.
And I think that Hubert is asking is if there will be always particles alive passing through the origin, right?
So the time the zero range needs to fill all the
but in infinite volume.
Yeah. Sorry, Pablo, I didn't.
Nothing. I was just interpreting Hubert's question.
Yeah.
Thank you.
More questions?
So
okay,
I have a question, if I can ask.
Go, Milton.
Yes.
So you mentioned something about the front and fast about this condition on the derivative, because I remember that in some of these Stefan problems, if at the boundary you arrive with the zero derivative, what happens is that the front is let's say
does not move.
Does not move until you get positive derivative.
Yes.
And then you move.
Yeah.
Right. Is that what happened also in this for your version of the Stefan problem?
Yes, I guess so. Yeah. So you need enough density to move the boundary. Yes, exactly. And this is why we were not able to treat this case. In fact, because so to understand the free boundaries, to define them x minus and x plus, we needed a strong sense of solutions to the PDE, and to have this strong sense of solutions, we needed the derivatives to be not zero, so free boundary to move exactly. So this is what I guess will happen. Yes.
Yeah. So being a little bit more precise, you can imagine, for example, that you have at your critical point that you have something like parabolic, no, going from 1/2 to 1 parabolically. And
I don't know.
Then you have to wait a little bit until you create the derivative at the boundary, and then you move.
Yeah. So in fact, with the conservation law, the derivative at the free boundaries is given. Okay, so you have a formula, an implicit formula for the speed of the interface. You have this. Yeah.
Okay. More questions? No? Okay.
May I ask another question? One extra quick question. So
yes, Milton, go.
So Marielle, I assume that monotonicity is very important, no, in the sense that this your facilitation is monotone in some sense.
Yes,
No?
because so the zero range is attractive, is what you mean?
Yeah. Because but I was wanted to say something else, because at the zero range level, for example, you still have this identification. If you for example put your condition is you need two guys to push you in order to move. Then you still have the
attractivity.
The attractivity, but you can imagine some more complicated interactions, no, that will give you attractivity, but will not give you monotonicity.
Okay.
In the sense that when you pass from the zero range process back to the exclusion, it's not completely straightforward how to do it.
No, of course not. At least to get at the hydrodynamic level, it is not obvious. But, so what was your question, in fact?
No, I mean, I was thinking about this. So you saw whether you thought about that type of dynamic. No, it was
no.
I mean, for example,
yeah, in Funaki strategy, the fact that you are able to characterize the stationary measures, you use the fact that the dynamics is monotonous. Yes.
Okay, but if you can characterize the stationary measures because you have this variation with the zero range, then you're okay, right?
Yes.
Because at the level of the zero range process, you can imagine more complicated facilitation dynamics, no? Because if you have a substrate, let's say, if you can have 4 particles instead of 1, then but then you can define some sort of dynamics. What happens if you have 4 particles at one side and 3 particles at the other? You cannot go over 4, but then maybe you can do something there. So I don't know. You didn't think about that, right?
No. We are more on the 2-dimensional version now,
okay.
Which is quite difficult.
Yeah. Okay, thank you.
Okay, a last question to Marielle. Don't fight.
Yeah, it's not. I'm going to. Yeah.
Are there questions or not?
No, I wanted to ask, but okay, maybe it's a bit late. Of asymmetric, if you introduce an asymmetry.
Yes. So the asymmetric case is handled more or less now by my postdoc in Lille, Linge, which tries to use the mapping also to treat the asymmetric case and to get hyperbolic equations. But yes, it has some hope that it's going to work.
Okay.
And we're also looking at the weekly asymmetric version of this with Guillaume Barracon and Oriane to get some KPZ equation also. This is also for Patrice and Milton. So and using again another mapping to get weekly ASEP, which makes this integrable. So this is why Guillaume Barracon is involved in this project. Because
what do you mean with the map? Like there is
another map.
Yes,
there is another map which can goes from the facilitated exclusion process to an exclusion process with a boundary.
Okay.
Yes, I can explain maybe another time because now it is quite late. But there is not, and also another mapping which passes from the facilitated process to the symmetric. To facilitated exclusion process to simple exclusion process with a boundary. And the boundary is the position of so it is represented by the first particle in the FEP.
Okay.
You can leave that when you visit us, Marielle.
Yes, exactly. Yes, it's also a good subject for the seminar.
Okay, so let's thank Marielle again.
Okay,
thank you, Marielle. Thank you so much.